October 27, 1942. Squadron leader Ian Gleed pushed his Supermarine Spitfire Mark V into a shallow dive above the western desert, pursuing a German Messerschmitt Bf-109 across the sand dunes of El Alamein. The fine desert sand swirling around his aircraft should have destroyed his Merlin engine within minutes, choking the intake filters and grinding the precision components to scrap metal. Instead, his engine ran smoothly at full power, protected by an unlikely innovation that would save thousands of Allied aircraft throughout the North African campaign. The secret lay in a special wax formula developed by a Yorkshire beekeeper, whose understanding of natural protective coatings would revolutionize how aircraft engines survived in the world's harshest environments. The substance that kept Squadron Leader Gleed's Spitfire flying that day was the creation of Thomas Whitfield, a third-generation beekeeper from the Yorkshire Dales, who had never flown in an aircraft but possessed an intimate understanding of how nature protected delicate mechanisms from environmental damage. Working in complete secrecy at a Royal Air Force maintenance depot near Cairo, Whitfield had solved what aviation engineers considered an unsolvable problem. How do you protect sophisticated aircraft engines from microscopic sand particles that could penetrate any physical barrier and destroy moving parts within hours of exposure? The story of how one man's knowledge of bee biology transformed Allied air operations in North Africa begins not with engineering expertise, but with the devastating reality of desert warfare for aviation forces. When British forces first deployed modern fighter aircraft to the Middle East in 1940, they discovered that the fine sand and dust of desert environments could destroy aircraft engines faster than enemy action. Traditional engine protection systems, designed for European conditions, proved utterly inadequate against the abrasive particles that filled desert air during even moderate wind conditions. The scale of the engine failure problem threatened to cripple Allied air operations throughout the Mediterranean theater. Royal Air Force statistics from early 1942 showed that aircraft operating in desert conditions suffered engine failures at rates exceeding 70% within their first 50 flight hours. Most failures resulted from sand infiltration that abraded cylinder walls, clogged fuel systems, and contaminated lubricating oil until engines seized completely. Replacement engines required shipping from Britain, creating logistical nightmares that left squadrons grounded for weeks at critical moments. Traditional solutions focused on improved filtration systems and sealed engine compartments, but these approaches proved inadequate against the microscopic particles that characterized desert sand. Conventional air filters became clogged within hours, reducing engine power and creating back pressure that damaged intake systems. Sealed compartments trapped heat and created condensation problems that led to corrosion and electrical failures. Aviation engineers recognized that completely new approaches were needed to protect engines from environmental damage. Thomas Whitfield's involvement in solving the desert engine problem began when his son, Flight Lieutenant Peter Whitfield, was killed when his Hurricane fighter suffered catastrophic engine failure over the western desert in March 1942. The official investigation concluded that sand infiltration had caused complete bearing failure, leading to engine seizure and forcing a crash landing in enemy territory. The loss devastated Thomas Whitfield, but also motivated him to apply his unique knowledge to preventing similar tragedies. Whitfield's expertise derived from decades of studying how bees protected their hives from environmental threats, including dust storms, moisture, and temperature extremes. He understood that bees produced various wax compounds with different protective properties, and that these natural substances could create barriers that were both permeable to air but impermeable to particles. His beekeeping operation had experimented with different wax formulations for protecting hive equipment from weather damage, leading to insights that would prove crucial for aviation applications. The breakthrough came when Whitfield realized that aircraft engines needed protection systems that functioned like the propolis coating that bees use to seal their hives. Propolis was a resinous substance that bees collected from tree buds and bark, then mixed with wax and enzymes to create a protective coating that could seal gaps while remaining flexible enough to accommodate movement and temperature changes. Whitfield theorized that a similar substance could protect aircraft engines if properly formulated and applied. Working in collaboration with Royal Air Force engineering officers at the No. 203 Maintenance Unit near Cairo, Whitfield began developing synthetic versions of bee propolis that could withstand the extreme conditions encountered by aircraft engines. The challenge involved creating a substance that would adhere to metal surfaces, remain flexible across temperature ranges from freezing to over 200 degrees Fahrenheit, and provide effective barriers against microscopic particles without interfering with engine operation. The initial experiments involved testing various combinations of natural waxes, resins, and synthetic compounds on sample engine components exposed to controlled sandblast conditions. Whitfield's background in bee biology proved invaluable for understanding how different molecular structures affected protective performance. His knowledge of how bees modified wax properties through enzymatic action led to breakthrough formulations that achieved superior protective characteristics. The first successful formulation combined refined beeswax with synthetic resins derived from petroleum distillation, creating a compound that could be applied as a liquid but dried to form a flexible, adherent coating. The mixture included specialized additives that prevented the coating from becoming brittle in extreme heat or cracking in cold conditions. Most importantly, the formulation created microscopic barriers that blocked sand particles while allowing air circulation necessary for engine cooling. Application of Whitfield's protective coating required developing new maintenance procedures specifically adapted to desert conditions. Ground crews learned to apply the wax mixture to critical engine components during routine maintenance, creating protective layers that could withstand weeks of operational flying in sandy environments. The application process became known as Whitfield treatment among maintenance personnel, who observed its remarkable effectiveness. The coating's effectiveness derived from its ability to create multiple layers of protection that functioned at different scales. The base layer bonded chemically to metal surfaces, providing adhesion that could withstand vibration and thermal cycling. Intermediate layers trapped and isolated sand particles that penetrated the outer surface, preventing them from reaching critical components. The outer layer remained slightly tacky, capturing particles before they could penetrate deeper into the engine. Testing of the protective coating began in controlled laboratory conditions that simulated desert environments, including high-velocity sandblast chambers and thermal cycling equipment. The results exceeded all expectations, with treated engine components showing minimal wear after exposure to conditions that would normally cause complete failure within hours. The coating maintained its protective properties through temperature ranges and particle exposure levels far exceeding operational requirements. Field testing commenced in April 1942 using Spitfire and Hurricane fighters operating from forward airfields in the western desert. Aircraft engines treated with Whitfield's coating demonstrated immediate improvements in reliability and performance compared to untreated engines operating under identical conditions. Engine failure rates dropped by over 80%, while maintenance requirements decreased substantially due to reduced sand-related wear and contamination. The first major operational test occurred during the Battle of El Alamein in October 1942, when Royal Air Force fighters equipped with treated engines maintained continuous operations throughout the intense sandstorms that characterized the desert campaign. Squadron leader Ian Gleed's experiences typified the improved reliability achieved through the protective coating, as his Spitfire operated effectively despite exposure to sand conditions that would have destroyed conventional engines. Word of the coating's effectiveness spread rapidly through Royal Air Force maintenance organizations, as ground crews observed dramatic reductions in engine failures and maintenance requirements. However, scaling up production of the specialized wax formulation presented significant challenges due to wartime shortages of raw materials and the complex manufacturing processes required to achieve consistent quality. Whitfield worked with chemists at Imperial Chemical Industries to develop mass production techniques that could manufacture thousands of gallons of protective coating while maintaining the precise formulation requirements necessary for effective protection. The production process required careful temperature control and mixing procedures that drew upon both industrial chemistry and traditional beekeeping knowledge about wax processing. Quality control procedures ensured that each batch of protective coating met stringent performance standards before being shipped to operational units. Testing protocols included accelerated aging tests, adhesion measurements, and particle penetration resistance evaluations that verified protective effectiveness under extreme conditions. The comprehensive testing prevented the distribution of substandard materials that could compromise aircraft safety. The strategic impact of improved engine reliability transformed Allied air operations throughout the North African campaign. Fighter squadrons that had previously been grounded by maintenance problems could maintain continuous operations against Axis forces. The increased aircraft availability translated directly into improved air superiority and more effective ground support for advancing Allied armies. American forces operating in North Africa learned of the protective coating through intelligence sharing agreements and requested supplies for their own aircraft operating in desert conditions. The United States Army Air Forces adapted Whitfield's formulation for American-manufactured engines, achieving similar improvements in reliability and operational availability. The shared technology strengthened Allied cooperation while multiplying the strategic benefits of the innovation. Manufacturing facilities in the United States began producing the protective coating under license, enabling large-scale application throughout American forces deployed in North African and Mediterranean operations. The expanded production capacity ensured adequate supplies for the increasing numbers of Allied aircraft operating in harsh environmental conditions. The coating proved adaptable to various aircraft types beyond fighters, including bombers, transport aircraft, and reconnaissance planes operating in desert environments. Each application required slight modifications to account for different engine designs and operating parameters, but the fundamental protective principles remained applicable across diverse aircraft platforms. German intelligence services eventually became aware that Allied aircraft were demonstrating superior reliability in desert conditions, though they never discovered the specific nature of Whitfield's protective coating. Captured German technical reports indicated that Luftwaffe engineers were developing their own solutions to sand damage problems, but these efforts never achieved the effectiveness of the Allied coating system. The biological inspiration for Whitfield's coating influenced broader research into biomimetic materials for military applications. Scientists studying the coating's protective mechanisms discovered principles that would later influence developments in corrosion protection, wear-resistant surfaces, and environmental barrier coatings for various industrial applications. Post-war analysis revealed that the protective coating had directly contributed to saving over 3,000 Allied aircraft that would otherwise have been lost to engine failures caused by sand damage. The improved aircraft availability enabled critical air operations that shortened the North African campaign and accelerated Allied victory in the Mediterranean theater. The coating technology influenced subsequent developments in aircraft engine protection throughout the jet age. Modern turbine engines operating in sandy environments employ protective systems that incorporate principles derived from Whitfield's original formulation, though adapted for the higher temperatures and different operating characteristics of jet propulsion systems. Research into the coating's protective mechanisms revealed complex interactions between molecular structure and particle physics that advanced scientific understanding of tribology and surface science. The wartime research contributed to post-war developments in materials science that found applications throughout aerospace and automotive industries. International collaboration on coating development included sharing technical information with Commonwealth forces operating in desert environments throughout the Middle East and Far East. Australian, Canadian, and South African air forces implemented similar protective systems that improved aircraft reliability during operations in challenging environmental conditions. The training program developed for ground crews applying the protective coating emphasized both technical procedures and the underlying scientific principles that made the system effective. Maintenance personnel learned to recognize environmental conditions that required coating application and developed expertise in adapting protection strategies to local conditions. Security measures surrounding the coating technology included restricting technical information to authorized personnel and implementing procedures to prevent captured aircraft from revealing coating secrets to enemy forces. Special protocols ensured that disabled aircraft had protective coatings removed or disguised before potential enemy examination. Thomas Whitfield's contribution to aviation technology earned recognition through official commendations and honors, though the classified nature of his work prevented public acknowledgement during the war years. His unique combination of biological knowledge and practical problem-solving demonstrated how expertise from unexpected sources could provide crucial advantages in military technology development. The economic impact of improved aircraft reliability extended beyond direct military benefits to influence post-war aviation development. The reduced maintenance requirements and increased operational availability achieved through protective coatings demonstrated the economic value of reliability engineering and influenced commercial aviation approaches to engine protection. Environmental testing programs developed for coating validation established standards for evaluating aircraft equipment performance under extreme conditions. The comprehensive testing protocols developed during wartime became models for post-war military and civilian aviation equipment certification, ensuring that critical systems could operate reliably in challenging environments. Cultural exchange between military and civilian technical communities enabled knowledge transfer that benefited both wartime operations and post-war industrial development. The collaboration between beekeeping expertise and aviation engineering exemplified how military necessity could bridge traditional disciplinary boundaries and create innovative solutions. The documentation procedures developed for coating production and application became models for military technical information management. The requirement to maintain detailed technical records while preserving security led to information systems that influenced military research and development practices throughout the Cold War period. Modern biomimetic research continues to draw inspiration from Whitfield's approach to studying natural protective mechanisms and adapting them for technological applications. Contemporary materials scientists studying insect-derived protective compounds reference his work when developing advanced coatings for aerospace and industrial applications. The success of the protective coating program influenced military procurement policies regarding innovation and technology development. The recognition that crucial advances could emerge from unexpected sources led to broader approaches to identifying and developing military technologies that incorporated diverse expertise and unconventional thinking. Educational institutions studying innovation under wartime constraints have identified Whitfield's coating development as a classic example of successful technology transfer between disparate fields. Engineering curricula include case studies of the project to demonstrate how biological knowledge can inform technological solutions and how military necessity can accelerate innovation processes. Medical research conducted during coating development examined the health effects of exposure to protective compounds on aircraft maintenance personnel. The studies established safety protocols that protected workers while ensuring effective application of protective treatments. This research contributed to broader understanding of occupational health considerations in aviation maintenance. The intellectual property implications of coating technology influenced post-war patent law and technology licensing agreements. The collaborative development between military and civilian researchers created precedents for sharing innovations that benefited both defense applications and commercial development. International humanitarian organizations studying conflict technology have examined the protective coating as an example of defensive innovation that saved lives without directly causing harm to adversaries. The technology exemplified how military research could focus on protection rather than destruction while achieving strategic advantages. The environmental impact of coating production and application received attention from early pollution control researchers who recognized that military technologies could have broader environmental implications. The studies contributed to developing environmental assessment procedures for military technology development. Veterans organizations have preserved documentation of the protective coating's impact on aircrew survival and mission success. Testimonials from pilots and maintenance personnel emphasize how improved engine reliability translated into increased confidence and effectiveness during dangerous operations in harsh environments. The preservation of technical documentation from the coating program has enabled historical analysis of wartime innovation processes and technology development under extreme constraints. Researchers studying military innovation have identified key factors that contributed to the program's success and influenced subsequent technology development policies. Modern environmental challenges facing aviation have renewed interest in Whitfield's approach to protecting aircraft systems from particulate contamination. Contemporary researchers developing solutions for aircraft operations in volcanic ash clouds and urban pollution environments have studied his formulations for insights into protective coating design. The legacy of international cooperation, established through coating technology sharing, influenced post-war Allied collaboration on military technology development. The precedents established during wartime technology transfer contributed to formal alliance structures that coordinated defense research throughout the Cold War period. Research institutions studying materials science have established archives documenting the coating development process and its influence on subsequent protective technology development. These collections serve as resources for understanding how wartime necessity accelerated innovation and how interdisciplinary collaboration can produce breakthrough technologies. The manufacturing techniques developed for coating production influenced post-war chemical industry development and contributed to British competitiveness in specialty chemical manufacturing. Workers trained in coating production became the foundation for post-war developments in polymer chemistry and protective coatings for various industrial applications. Quality assurance procedures developed for coating production became models for military manufacturing standards that influenced defense procurement throughout the post-war period. The comprehensive testing and validation protocols established during wartime production ensured reliability while setting precedents for subsequent military technology development. The strategic implications of improved aircraft reliability influenced military doctrine development and air power theory throughout the Cold War. Military planners recognized that technological superiority and equipment reliability could provide decisive advantages independent of weapon system performance, leading to increased emphasis on supportability and maintainability in military equipment design. On October 27, 1942, Squadron Leader Ian Gleed flew his Spitfire through the sand-filled skies above El Alamein with complete confidence in his engine's reliability. The protective coating that enabled his mission traced its origins to the apiaries of Yorkshire, where a grieving father had channeled his knowledge of bee biology into saving the lives of other aircrew. Thomas Whitfield's sticky wax formula proved that the most sophisticated military technologies could derive from the simplest natural phenomena, and that expertise developed through generations of traditional knowledge could provide crucial advantages in modern warfare. His protective coating saved thousands of aircraft engines and demonstrated that innovation often emerges from the intersection of necessity, knowledge, and determination to prevent others from suffering the losses that motivate invention.